Hi, welcome back to Easy Maths by Dr. Nasir, your path to maths confidence. Don't forget to share, like, and subscribe so you never miss a conceptual concrete lesson. Well, in today's lecture, we will see some exercises related to first order linear ODEs and initial value problems. We'll see an exercise. Find the general solution of the ODE dr by d theta plus r secant theta is equal to cosine theta, where theta belongs to omega, which is defined as r other than 4k plus minus 1 into pi by 2, where k belongs to z. Determine whether there is any transient term in the general solution. Well, see solution. The given ODE 1.1 is a first order linear ODE independent variable r. Comparing the ODE 1.1 with standard form, we have p of theta is equal to secant theta, where theta belongs to omega. So integrating factor is mu of theta is equal to exponential of integral of p of theta d theta, which is equal to exponential of integral of secant theta d theta, which is equal to exponential log of secant theta plus tangent theta absolute. So mu of theta is equal to secant theta plus tangent theta absolute, where theta belongs to omega. Multiplying the ODE 1.1 by the integrating factor, we have secant theta plus tangent theta absolute into dr by d theta plus r secant theta into secant theta plus tangent theta absolute is equal to cosine theta into secant theta plus tangent theta absolute, where theta belongs to omega. Now for theta belongs to omega plus, which is equal to union over k belongs to z of open intervals 4k minus 1 into pi by 2 up to 4k plus 1 into pi by 2. Secant theta plus tangent theta absolute is equal to secant theta plus tangent theta. Therefore, from equation 1.2 we have secant theta plus tangent theta into dr by d theta plus r secant theta into secant theta plus tangent theta is equal to cosine theta into secant theta plus tangent theta, where theta belongs to omega plus. So we have secant theta plus tangent theta into dr by d theta plus r into secant theta plus secant theta into tangent theta is equal to 1 plus sine theta, where theta belongs to omega plus. Well, this can be expressed as d by d theta of secant theta plus tangent theta into r is equal to 1 plus sine theta, where theta belongs to omega plus. So we have d of secant theta plus tangent theta into r is equal to 1 plus sine theta d theta, where theta belongs to omega plus. Now integrating, we have integral of d of secant theta plus tangent theta into r is equal to integral of 1 plus sine theta d theta plus c, where theta belongs to omega plus and c is arbitrary constant. So we have secant theta plus tangent theta into r is equal to theta minus cosine theta plus c, where theta belongs to omega plus and c belongs to r. So we have r of theta is equal to theta minus cosine theta plus c over secant theta plus tangent theta, where theta belongs to omega plus and c is arbitrary constant. Also for theta belongs to omega minus, which is omega other than omega plus, secant theta plus tangent theta absolute is equal to minus secant theta plus tangent theta. Therefore, from equation 1.2 we have minus secant theta plus tangent theta into dr by d theta. Secant theta into secant theta plus tangent theta is equal to minus cosine theta into secant theta plus tangent theta, where theta belongs to omega minus. So we have secant theta plus tangent theta into dr by d theta plus r into secant square theta plus secant theta into tangent theta is equal to 1 plus sine theta, where theta belongs to omega minus. Well, this can be expressed as d by d theta of secant theta plus tangent theta into r is equal to 1 plus sine theta, where theta belongs to omega minus. So we have d of secant theta plus tangent theta into r is equal to 1 plus sine theta into d theta, where theta belongs to omega minus. Now taking integral, we have integral of d of secant theta plus tangent theta into r is equal to integral of 1 plus sine theta d theta plus c, where theta belongs to omega minus and c is arbitrary constant. So secant theta plus tangent theta into r is equal to theta minus cosine theta plus c, where theta belongs to omega minus and c is arbitrary constant. So r of theta is equal to theta minus cosine theta plus c over secant theta plus tangent theta, where theta belongs to omega minus and c is arbitrary constant. Thus from equations 1.3 and 1.4 we have r of theta is equal to theta minus cosine theta plus c over secant theta plus tangent theta, where theta belongs to omega and c is arbitrary constant, which is the required general solution and it does not contain any transient term. Well, see another exercise. Find the general solution of the ODE dq by dt plus 2tq is equal to q plus 4t minus 2 where t belongs to R. Determine whether there is any transient term in the general solution. Well, see solution. The ODE 1.5 can be expressed as dq by dt plus 2q minus 1 into q is equal to 2 into 2t minus 1 where t belongs to R, which is the first order linear ODE independent variable q. Comparing the ODE 1.6 with standard form, we have p of t is equal to 2t minus 1 where t belongs to R. Comparing the ODE 1.6 with standard form, we have p of t is equal to 2t minus 1 where t belongs to R. So integrating factor is mu of t is equal to exponential of integral of p of t dt, which is equal to exponential of integral of 2t minus 1 into dt. So mu of t is equal to exponential of t square minus t where t belongs to R. Multiplying the ODE 1.6 by integrating factor, we have exponential of t square minus t dq by dt plus 2t minus 1 into exponential of t square minus t into q is equal to 2 into 2t minus 1 into exponential of t square minus t where t belongs to R. Well, this can be expressed as d by dt of exponential of t square minus t into q is equal to 2 into 2t minus 1 into exponential of t square minus t where t belongs to R. So we have d of exponential of t square minus t into q is equal to 2 into 2t minus 1 into exponential of t square minus t dt where t belongs to R. Taking integral, we have integral of d of exponential of t square minus t into q is equal to 2 into integral of 2t minus 1 into exponential of t square minus t dt plus c where t belongs to R and c is arbitrary constant. So we have exponential of t square minus t into q is equal to 2 into exponential of t square minus t plus c where t belongs to R and c is arbitrary constant. So q of t is equal to 2 plus c exponential of minus t into t minus 1 where t belongs to R and c is arbitrary constant, which is the required general solution and contains the transient term exponential of minus t into t minus 1. We'll see another exercise. Find the general solution of the ODE x dy by dx plus 3x plus 1 into y is equal to exponential of minus 3x where x belongs to R other than 0. Determine whether there is any transient term in the general solution. We'll see solution. The ODE 1.7 can be expressed as dy by dx plus 3 plus 1 over x into y is equal to exponential of minus 3x over x where x belongs to R other than 0. Comparing the ODE 1.8 with standard form, we have p of x is equal to 3 plus 1 over x where x belongs to R. So integrating factor is mu of x is equal to exponential of integral of p of x dx, which is equal to exponential of integral of 3 plus 1 over x dx, which is equal to exponential of 3x plus log of x absolute. So mu of x is equal to x absolute into exponential of 3x where x belongs to R other than 0. Multiplying equation 1 by 8 by integrating factor, we have x absolute into exponential of 3x dy by dx plus x absolute into exponential of 3x into 3 plus 1 over x into y is equal to x absolute over x where x belongs to R other than 0. Now for x belongs to minus infinity to 0, open double, x absolute is equal to minus x. Therefore from equation 1.9 we have minus x exponential of 3x dy by dx minus x exponential of 3x into 3 plus 1 over x into y is equal to minus x over x where x belongs to minus infinity to 0, open interval. So we have x exponential of 3x dy by dx plus x exponential of 3x into 3 plus 1 over x into y is equal to x over x where x belongs to minus infinity to 0, open interval. Well, this can be expressed as x exponential of 3x dy by dx plus 3x plus 1 into exponential of 3x into y is equal to 1 where x belongs to minus infinity to 0, open interval. So we have d by dx of x exponential of 3x into y is equal to 1 where x belongs to minus infinity to 0, open interval. So we have d of x exponential of 3x into y is equal to dx where x belongs to minus infinity to 0, open interval. Taking integral, we have integral of d of x exponential of 3x into y is equal to integral of dx plus c where x belongs to minus infinity to 0, open interval and c is arbitrary constant. So we have x exponential of 3x into y is equal to x plus c where x belongs to minus infinity to 0, open interval and c is arbitrary constant. Dividing this equation by x exponential 3x, we have y of x is equal to s plus c over x exponential 3x, where s belongs to -infinity to 0, open interval, and c is the arbitrary constant. Also for s belongs to 0 to plus infinity, open interval, x absolute is equal to x. Therefore, from equation 1.9, we have x exponential 3x divided by dx plus x exponential 3x into 3 plus 1 over s into y is equal to x over s, where s belongs to 0 to plus infinity, open interval. So we have x exponential 3x divided by dx plus 3x plus 1 into exponential 3x into y is equal to 1, where s belongs to 0 to plus infinity, open interval. Well, this can be expressed as d by dx of x exponential 3x into y is equal to 1, where x is equal to 0 to plus infinity, open interval. So we have d of x exponential 3x into y is equal to dx, where x is equal to 0 to plus infinity, open interval. Taking integral, we have integral of d of x exponential 3x into y is equal to integral of dx plus c, where x is equal to 0 to plus infinity, open interval, and c is the arbitrary constant. So we have x exponential 3x into y is equal to s plus c, where s belongs to 0 to plus infinity, and c is the arbitrary constant. Dividing this by x exponential 3x, we have y of x is equal to s plus c over x exponential 3x, where s belongs to 0 to plus infinity, open interval, and c is the arbitrary constant. Thus, from equations 1.10 and 1.11, we have y of x is equal to s plus c over x exponential 3x, where s belongs to r other than 0, and c is the arbitrary constant, which is a required general solution and contains transient terms 1 over exponential 3x and 1 over x exponential 3x. We'll see another exercise. Find the general solution of the ODE sk minus 1 into dy by dx plus 2y is equal to s plus 1 square, where s belongs to r other than -1 and 1. Determine whether there is any transient term in the general solution. We'll see solution. The ODE 1.12 can be expressed as dy by dx plus 2 over sk minus 1 into y is equal to s plus 1 square over s square minus 1, where s belongs to r other than -1, 1. Well, this can be expressed as dy by dx plus 2 over s square minus 1 into y is equal to s plus 1 square over x minus 1 into s plus 1, where s belongs to r other than -1, 1. So we have dy by dx plus 2 over s square minus 1 into y is equal to s plus 1 over s minus 1, where s belongs to r other than -1, 1. Comparing the ODE 1.13 with standard form, we have p of x equal to 2 over s square minus 1, where s belongs to r other than -1, 1. So integrating factor is mu x is equal to exponential of integral of ps dx, which is equal to exponential of integral of 2 over s square minus 1 dx, which is equal to exponential log of s minus 1 over s plus 1 absolute. So mu x is equal to s minus 1 over s plus 1 absolute, where s belongs to r other than -1, 1. Multiplying equation 1/13 by integrating factor, we have s minus 1 over s plus 1 absolute into dy by dx plus s minus 1 over s plus 1 absolute into 2 over s square minus 1 into y is equal to s minus 1 over s plus 1 absolute into s plus 1 over s minus 1, where s belongs to r other than -1, 1. Now for s belongs to -50 to -1, open interval, s minus 1 over s plus 1 absolute is equal to s minus 1 over s plus 1. Therefore, from 1.14 we have s minus 1 over s plus 1 into dy by dx plus s minus 1 over s plus 1 into 2 over s square minus 1 into y is equal to s minus 1 over s plus 1 into s plus 1 over s minus 1, where s belongs to -50 to -1, open interval. So we have s minus 1 over s plus 1 into dy by dx plus s minus 1 over s plus 1 into 2 over s minus 1 into s plus 1 into y is equal to 1, where s belongs to -50 to -1, open interval. So we have f minus 1 over s plus 1 into dy by dx plus 2 over s plus 1 square into y is equal to 1, where s belongs to -50 to -1, open interval. Well, this can be expressed as d by dx of s minus 1 over s plus 1 into y is equal to 1, where s belongs to -infinity to -1, open interval. So we have d of s minus 1 over s plus 1 into y is equal to dx, where s belongs to -infinity to -1, open interval. Taking integral, we have integral of d of s minus 1 over s plus 1 into y is equal to integral of ds plus c, where s belongs to -infinity to -1, open interval, and c is arbitrary constant. So we have s minus 1 over s plus 1 into y is equal to s plus c, where s belongs to -infinity to -1, open interval, and c is arbitrary constant. So y of x is equal to s plus 1 into s plus c over s minus 1, where s belongs to -infinity to -1, open interval, and c is arbitrary constant. Further, for s belongs to minus 1 to 1 open interval, s minus 1 over s plus 1 absolute is equal to minus s minus 1 over s plus 1. Therefore, from equation 1.14 we have minus s minus 1 over s plus 1 into dy by dx minus s minus 1 over s plus 1 into 2 over sk minus 1 into y is equal to minus s minus 1 over s plus 1 into s plus 1 over s minus 1, where s belongs to minus 1 to 1 open interval. So we have s minus 1 over s plus 1 into dy by dx plus s minus 1 over s plus 1 into 2 over s minus 1 into s plus 1 into y is equal to 1, where s belongs to minus 1 to 1 open interval. So we have s minus 1 over s plus 1 into dy by dx plus 2 over s plus 1 square into y is equal to 1, where s belongs to minus 1 to 1 open interval. So d by dx of s minus 1 over s plus 1 into y is equal to 1, where s belongs to minus 1 to 1 open interval. Well, this can be expressed as d of s minus 1 over s plus 1 into y is equal to dx, where s belongs to minus 1 to 1 open interval. Taking integral, we have integral of d of s minus 1 over s plus 1 into y is equal to integral of dx plus c, where s belongs to minus 1 to 1 open interval and c is arbitrary constant. So we have s minus 1 over s plus 1 into y is equal to s plus c, where s belongs to minus 1 to 1 open interval and c is arbitrary constant. So y of x is equal to s plus 1 into s plus c over s minus 1, where s belongs to minus 1 to 1 open interval and c is arbitrary constant. Also for s belongs to 1 to plus infinity, x minus 1 over s plus 1 absolute is equal to s minus 1 over s plus 1. Therefore, from equation 1.14 we have s minus 1 over s plus 1 into dy by dx plus x minus 1 over s plus 1 into 2 over sk minus 1 into y is equal to x minus 1 over s plus 1 into s plus 1 over s minus 1, where s belongs to 1 to plus infinity open interval. So we have s minus 1 over s plus 1 into dy by dx plus s minus 1 over s plus 1 into 2 over s minus 1 into s plus 1 into y is equal to 1, where s belongs to 1 to plus infinity open interval. So we have s minus 1 over s plus 1 into dy by dx plus 2 over s plus 1 square into y is equal to 1, where s belongs to 1 to plus infinity open interval. Well, this can be expressed as d by dx of s minus 1 over s plus 1 into y is equal to 1, where s belongs to 1 to plus infinity open interval. This can be expressed as d of s minus 1 over s plus 1 into y is equal to dx, where s belongs to 1 to plus infinity open interval. Taking integral, we have integral of d of s minus 1 over s plus 1 into y is equal to integral of ds plus c, where s belongs to 1 to plus infinity open interval and c is arbitrary constant. So s minus 1 over s plus 1 into y is equal to s plus c, where s belongs to 1 to plus infinity open interval and c is arbitrary constant. So y of x is equal to s plus 1 into s plus c over s minus 1, where s belongs to 1 to plus infinity open interval and c is arbitrary constant. Thus, from equation 1.15, 1.16 and 1.17 we have y of x is equal to s plus 1 into s plus c over s minus 1, where s belongs to r other than minus 1, 1 and c is arbitrary constant, which is a required general solution and it does not contain any transient term. Well, see another exercise. Find solution of the initial variable problem s d by dx plus y is equal to exponential x, where s belongs to r other than 0 and y of 1 is equal to. Also state the interval I subset of R over which the solution is defined. We will see solution. The ODE 1.18 can be expressed as dy by dx plus y over x is equal to exponential x over x, where x belongs to r other than 0. Comparing the ODE 1.19 with standard form, we have p of x is equal to 1 over x, where x belongs to r other than 0. So integrating factor is mu of x is equal to exponential of integral of p of s dx, which is equal to exponential of integral of 1 over s dx, which is equal to exponential log of x absolute. So mu of x is equal to x absolute, where x belongs to r other than 0. Multiplying equation 1.19 by integrating factor, we have x absolute divided by ds plus x absolute over x into y is equal to x absolute exponential x over x, where x belongs to r other than 0. Now for x belongs to minus to 0 open interval, x absolute is equal to minus x. Therefore, from equation 1.20 we have minus x divided by dx minus x over x into y is equal to minus x exponential x over x, where x belongs to minus infinity to 0 open interval. So x divided by dx plus x over x into y is equal to x exponential x over x, where x belongs to minus infinity to 0 open interval. So we have x divided by dx plus y is equal to exponential x, where x belongs to minus infinity to 0 open interval. Well, this can be expressed as d by dx of xy is equal to exponential x, where x belongs to minus infinity to 0 open interval. So we have d of sy is equal to exponential s dx where s equal to minus infinity to 0 open double. Taking integral, we have integral of d of sy is equal to integral of exponential s dx plus c where s equal to minus infinity to 0 open double and c is the arbitrary constant. So we have xy is equal to exponential s plus c where s equal to minus infinity to 0 open double and c is the arbitrary constant. So y of x is equal to exponential s plus c over s where s equal to minus infinity to 0 open double and c is the arbitrary constant. Also for s equal to 0 to plus infinity open double x absolute is equal to x. Therefore from equation 1.20 we have x divided by dx plus x over x into y is equal to x exponential x over x where s equal to 0 to plus infinity open double. So we have x divided by dx plus y is equal to exponential x where s equal to 0 to plus infinity open double. Well, this can be expressed as d by dx of sy is equal to exponential x where s equal to 0 to plus infinity open interval. So d of xy is equal to exponential s ds where s equal to 0 to plus infinity open interval. Taking integral, we have integral of d of sy is equal to integral of exponential s ds plus c where s equal to 0 to plus infinity open interval and c is arbitrary constant. So xy is equal to exponential s plus c where s equal to 0 to plus infinity open interval and c is arbitrary constant. So y of x is equal to exponential x plus c over x where x equal to 0 to plus infinity open interval and c is arbitrary constant. Next from equations 1.21 and 1.22 we have y of x is equal to exponential x plus c over x where x equal to r other than 0 and c is the arbitrary constant, which is a general solution of the ODE 1.18. Now using the initial condition 1.18 that is y of 1 is equal to, we have y of 1 is equal to exponential of 1 plus c over 1. So we have 2 is equal to e plus c. Therefore, y of x is equal to exponential minus e plus 2 over x, where x equal to 0 to plus infinity open interval, which is a solution of the initial value problem 1.18 and is defined over I is equal to 0 to plus infinity open interval. Let's see another exercise. Find solution of the initial value problem y ds per dy minus x is equal to 2y square, where y belongs to r other than 0, and initial condition is y of 1 is equal to 5. Also state the interval I is subset of R over which the solution is defined. Well, see solution. Now ODE 1.23 can be expressed as ds by dy minus x over y is equal to y, where y belongs to R other than 0. Comparing the ODE 1.24 with standard form, we have p of y is equal to minus 1 over y, where y belongs to R other than 0. So integrating factor is mu of y is equal to exponential of integral of p of y dy, which is equal to exponential of integral of minus 1 over y dy, which is equal to exponential of minus log of y absolute, which is equal to exponential log of y absolute exponent minus 1, which is equal to y absolute exponent minus 1. So mu of y is equal to 1 over y absolute, where y belongs to r other than 0. Multiplying equation 1.24 by integrating factor, we have 1 over y absolute ds by dy minus 1 over y absolute x over y is equal to 2 into y over y absolute, where y belongs to r other than 0. Now for y belong to minus infinity to 0 open interval, y absolute is equal to minus y. Therefore from equation 1.25 we have minus 1 over y ds by dy minus 1 over minus y into x over y is equal to minus 2 into y over y, where y belong to minus infinity to 0 open interval. So 1 over y ds by dy minus x over y square is equal to, where y belong to minus infinity to 0 open interval. Well, this can be expressed as d by dy of x over y is equal to, where y belongs to minus infinity to 0 open interval. So we had d of x by y is equal to 2 dy where y belongs to minus infinity to 0 open interval. Taking integral, we have integral of d of x over y is equal to integral of 2 dy plus c, where y belongs to minus infinity to 0 open interval and c is arbitrary constant. So x over y is equal to 2y plus c, where y belongs to minus infinity to 0 open interval and c is arbitrary constant. So x over y is equal to 2y square plus cy, where y belongs to minus infinity to 0 open interval and c is arbitrary constant. Also for y belongs to 0 to plus infinity, y absolute is equal to y. Therefore from equation 125 we have 1 over y ds by dy minus 1 over y into x over y is equal to 2 into y over y, where y belongs to 0 to plus infinity open interval. So we have 1 over y ds by dy minus x over y square is equal to 2, where y belongs to 0 to plus infinity open interval. So we have d by dy of x or y is equal to, where y belongs to 0 to plus infinity open interval. So d of x or y is equal to 2 dy where y belongs to 0 to plus infinity open interval. Taking integral, we have integral of d of x or y is equal to integral of 2 dy where y belongs to 0 to plus infinity open interval. So we have x or y is equal to 2y plus c where y belongs to 0 to plus infinity open interval and c is the arbitrary constant. So x of y is equal to y square plus cy where y belongs to 0 to plus infinity open interval and c is the arbitrary constant. Thus from equations 1.26 and 1.27 we have x of y is equal to y square plus cy where y belongs to r other than 0 and c is the arbitrary constant, which is general solution of the ODE 1.23. Now using the initial condition 1.23, that is y of 1 is equal to 5, we have 1 is equal to 2 into 5 square plus c into 5. So we have 1 equal to 50 plus 5c. So c is equal to minus 49 by 5. Therefore s of y is equal to y square minus 49 by 5 into y, where y belongs to 0 to plus infinity open interval, which is the solution of the initial value problem 1.23 and is defined over I is equal to 0 to plus infinity open interval. Well, see another exercise. Find solution of the initial value problem L di by dt plus R I is equal to E, where t belongs to R, I of 0 is equal to I naught, where L, R, E and I naught are constants and L is non-zero. Also state the interval I subset of R over which the solution is defined. Well, see solution. The ODE 1.28 can be expressed as di by dt plus R over L into I is equal to E over L, where t belongs to R. Comparing the ODE 1.29 with standard form, we have P of t is equal to R over L, where t belongs to R. So integrating factor is mu of t is equal to exponential of integral P of t dt, which is equal to exponential integral of R over L dt. So mu of t is equal to exponential of R over L into t, where t belongs to R. Multiplying equation 1.29 by integrating factor, we have exponential of R over L into t di by dt plus R over L into exponential of R over L into t into I is equal to E over L exponential of R over L into t, where t belongs to R. Well, this can be expressed as d by dt of exponential of R over L into t into I is equal to E over L exponential of R over L into t, where t belongs to R. Well, this can be expressed as d of exponential R over L into t into I is equal to E over L into exponential R over L into t dt, where t belongs to R. Taking integral, we have integral of d of exponential R over L into t into I is equal to integral of E over L exponential R over L into t dt plus c, where t belongs to R and c is the arbitrary constant. So we have exponential R over L into t into I is equal to E over L exponential of R over L into t over R over L plus c, where t belongs to R and c is the arbitrary constant. So we have exponential R over L into t into I is equal to E over R exponential R over L into t plus c, where t belongs to R and c is the arbitrary constant. So I of t is equal to E over R plus c exponential minus R over L into t, where t belongs to R and c is the arbitrary constant, which is general solution of the ODE 1.28. Now using the initial condition 1.28, that is I of 0 is equal to I naught, we have I of 0 is equal to E over R plus c exponential minus R over L into 0. So we have I naught is equal to E over R plus c, which implies that c is equal to I naught minus E over R. Therefore I of t is equal to E over R plus I naught minus E over R into exponential minus R over L into t, which is the solution of the initial value problem 1.28 and is defined over I is equal to R. That's it for today. Well, in the next lecture, we will see some more exercises related to first order initial value problems. Don't forget to share, like and subscribe Easy Math by Dr. Nasir so you never miss a conceptual concrete lesson.